Good morning, everyone. This is Robert Haynes here with the National Weather Service in Burlington. We will get started around the top of the hour. So welcome all to those joining in. We'll get started in about 5 minutes. Good morning and welcome to those joining in. This is Robert Haynes. We'll get started in a couple minutes on our advanced Skywarn course here. We'll start near the top of the hour. All right, the clock has hit 10 here, so we will go ahead and get started. Good morning and welcome, everyone. Thanks for taking part of your Saturday morning to spend some time learning a little bit about some more advanced stuff regarding our radar, especially, is going to be some of the main topics we're going to talk about. But just to give you a little bit of a look into our severe weather operations and what that all looks like. So we'll go over some of the radar, what we have in our toolkit, some of the unique functions that are available to us thanks to dual pole and multi-radar, multi-sensor, or what we simply call MRMS. We'll talk about thunderstorm evolution and how we do that once we get into severe weather operations. Some of the uses of satellites. Satellites are really helpful in a lot of ways in supplementing radar operations. And then we'll do a couple case reviews to apply some of the things we look at for radar. So just as a quick reminder, this is the area that we service. We service the 4 northernmost counties of New York: St. Lawrence, Franklin, Clinton, and Essex counties. And then we cover most of Vermont. We still don't cover Bennington and Windham. So those will be handled by National Weather Service Albany. But we cover essentially Vermont and then the 4 northernmost counties of New York, covering a wide variety of terrain features from the St. Lawrence Valley to the Adirondack Mountain Range, the Champlain Valley, north central Vermont, which is kind of has the Green Mountains along the dividing line between the Champlain Valley and it, as well as a lot of rolling hills and rivers. The Northeast Kingdom, kind of a similar geographical makeup as the north central Vermont, and then of course south central Vermont, where the Green Mountains and the Appalachians meet. So to help us with our severe weather operations, we've got many screens to employ. We can cover a lot of ground on our different screens and monitors to help us analyze severe weather. Usually when it comes to severe weather operations, I've got displays of forecasts and other things, but usually when it comes to actually running the radar desk and being the person to issue severe weather warnings, typically all of the monitors are devoted to some level of just being able to look at severe weather off of each of those individual screens. So it's all about working with what we've got. Pretty much anything and everything that we use is made to help us on severe weather days. We're still looking at surface observations. We're still looking at upper air observations, looking at computer models, whereas usually we focus on most of our weather systems on a global scale. Really, when we get to the nitty gritty, when we get to severe weather operations, we're still using computer models, but those that are kind of embedded within there, that are nested and focused over just a small core area that can run at a very high resolution to determine storm evolution, and then watching satellite imagery and the radar for the trends that we see therein. So the surface observations are very important. We're still looking at each of the wind temperatures, what the cloud cover's like, and the precipitation and the visibility, all because that helps us to do things like create our weather maps that help us place frontal boundaries. So each of those parameters are important to be able to highlight features. And so this particular feature, this was on, I think it was like some day like towards the end of October, where you had a very clearly defined warm front, where just to the north of it, you've got a lot of temperatures in the 50s, some even 40s, where to the south, you've got a lot of 70s and then even a few 80s lifting north into this area. And so you can see with the southeast flow against north winds, you had just very strong convergence along the international border. And on this day, we had a number of hail reports up in the northern St. Lawrence Valley. I think we had a couple severe storms that occurred somewhere here in the Champlain Valley. And then of course we had a lot of heavy rain occur in between in this type of setup here. So all of these different features we use to help us pinpoint where severe weather will happen based off of those surface observations. If you've listened to any of our Skywarn presentations, you've seen our information about how we use weather balloons. And of course, one of those features is whether or not storms are possible. So when it comes to severe weather day, we will be analyzing these forecast soundings to determine if the environment is unstable and ready to develop thunderstorms. So of course you have the green line representing your dew point. You've got your red line representing just your temperature. And when you get to what's here known as the level of free the condensation level, and the level of free convection, it's kind of obscured there a little bit. They're overlapping. When you get that, then you run parcels of air relative to, it looks like this image is a little too low resolution to check, but you run it first against a dry adiabatic lapse rate until you've reached that level, and then you can run off the moist adiabat. And so then all of this area that runs in between this little profile of this dotted dashed red line, all of this is what we meteorologists refer to as CAPE. And so when we see a great amount of distance between this red line and the dotted red line, that indicates that you have large CAPE profiles. And so usually this is helpful for thunderstorms to develop. And one of the things that we look for is there plenty of dry air in the layer? If you have plenty of dry air, that usually is reflected as strong winds at the surface when there's a thunderstorm downburst. And then we also, of course, look at these profiles here. Do we have plenty of shear in the environment as well? So soundings are very important for us to analyze the thunderstorm's environment. And so it's one of the key tools that we have when it comes to severe weather day. And of course, our most relevant tool is going to always be our radar. Our radar is rotating, and usually, no matter the scanning pattern that we use, it's going to rotate about every 4 to 5 minutes. So each 4 to 5 minutes, we get an update on what is happening at each layer of the atmosphere as the radar continues to spin and look a little bit higher up into the atmosphere. It gives us a complete picture of what's happening because, of course, we have a lot of beam blockage here. So out in the plains, you can run the half-degree tilt, the lowest level, and have a good view of the thunderstorms that might be happening. You might have good view of rotation. Here, that's not as much the case just with the beam blockage. Our mountains make it difficult to be able to see what's happening in the lowest levels in the Northeast Kingdom, but also even Rutland and Windsor County sometimes, as well as the St. Lawrence Valley. So we do really need spotters still. Spotters are always going to be an important part of our severe weather operations because they're going to be able to see wall clouds and things like that a little bit better than our radar can. So as we start diving into the radar segment of the presentation this morning, I think there's one important thing that I also want to highlight here is how the radar starts to lose its vision a little bit as you get a little further and further out. So you have, as the radar is spinning, it's sending out these electromagnetic pulses. And so close to the radar, the gap of that is really thin. But as you get further and further out, that gap is going to increase. And so what it's able to resolve is going to be a little bit less. It's going to be a little murkier, the picture in there. So say storm B might be tornadic, but it's going to have poor resolution. If the mesocyclone in there is really small, it may not be able to resolve that feature in that storm. And of course, the other thing is because we have to send the radar beam at an angle so as to avoid the Earth's curvature, the result of that is that storms further out, the lower levels of those thunderstorms, they're not going to be captured by the radar image as well. However, you have the opposite situation with storm A. In the case of storm A, yeah, we might be able to see if there is rotation, but we might not be able to see features like hailstones that might be up in the thunderstorm. So there's a lot of limitations to radar, but they are very important to be able to determine that. That little area where it can be a little difficult to see what's happening in the thunderstorm is known as the cone of silence. I know sometimes we'll get a lot of questions like, what's that big black dot near where the radar is? And that's just simply to mark that that's where the cone of silence is. So radar only goes up to a 19.5 degree tilt as far as what it looks at. That's typically going to be about the tops of where your thunderstorms can go. It's usually not very beneficial in looking at thunderstorms to look straight up, and it also requires more mechanical parts to be able to view that. So in general, it's best to excuse me, scan between the 1/2 and the 19.5 degree tilt. So the Doppler radar, most will go between 1/2 and 19.5, but there are different radar systems out there. There's the terminal weather Doppler, which is usually used by airports, hence the name terminal, that since they're most concerned with landing and taking off planes, usually only look at the lowest scans. They actually even have like a 0.3 degree tilt usually. And then there are also, since we're so close to the Canadian border, we also benefit from the Canadian radar system, which is a little bit different than our system, and they start their scans at the 0.4 degree. And that makes even a world of difference as far as what they're able to view at the lowest scan. Sometimes we can see things very clearly in the St. Lawrence Valley, thanks to how low that radar is. And so we often rely on that as well. So satellites help to screen for severe storms in a lot of ways that radar might not be able to. Satellites are helpful in showing us a storm's evolution, oftentimes even before something appears on the radar scan. So we get satellite pictures every 3 to 5 minutes, so that sometimes is faster than radar. Additionally, it has the capability of running different mesosectors, so you can even get it minute by minute. So you can get better time resolution on satellite than even radar. So we can get even faster scans to be able to distinguish details about storms, and we can even look at features like global lightning mappers. We can sometimes see lightning flashing via satellite before any lightning network captures anything. The only issue with Global Lightning Mapper is that it's runs based off of a background file of like the general brightness of the atmosphere. And then it uses, if there's like a sudden brightening in those pixels of the background field, it detects that as lightning. And so it's somewhat accurate, but it's not able to like pinpoint the specific location. But when decision makers want to know if lightning is about to hit, say, a fairgrounds, sometimes Global Lightning Mapper can give us a 2 to 3 extra minute lead time on making those type of calls. Also, lightning jumps, any sudden increases in lightning is typically indicative of a strong updraft in a thunderstorm. And so usually we'll look at things like Global Lightning Mapper to detect things like whether a thunderstorm is developing maybe quicker than what might be seen on radar. So there's a lot of supplemental resources that satellites use. We don't often use satellite to make the decision to post severe thunderstorm warnings or tornado warnings, but it really does help us analyze a thunderstorm and how it's going. And so that's kind of the technology side of things. We have our surface observations, which we use to create maps, get a sense of where boundaries are located. We've got our radar and our satellites to analyze minute by minute changes. So kind of looking a little bit as a way of review on our severe weather operations and how we start gearing the messaging for it. The first place we might mention severe weather is going to often be things like the hazardous weather outlook. Usually that is just a heads up of, hey, we're noticing something, there's some potential out there in the future. It may be useful to check your action plans and see if a shelter is ready. The watch phase is usually when it's time to start monitoring conditions. That's the point where we start seeing ingredients lining up. That's usually the point where it's time to, I guess, start keeping an eye on the sky, start watching your trusted news sources, checking weather.gov, seeing if there are any warnings up there, tuning up your NOAA weather radios, all those type of things. And then, of course, the warning covers the idea of, all right, your storm is imminent, your storm is happening. So watch, it's in the future, not quite there yet. And the warning is the like, okay, this is happening right now. And then your actions in that time in matters of seconds can save lives. So a brief overview as we discuss severe weather operations is just a reminder of the climatology of severe weather in our region. The height of the severe season is summer. So we now being in July are in our peak severe weather season. We have more daytime heating at this time of year, and so that generates greater surface instability. We've got the Bermuda high, and the Bermuda high this year has been quite strong. And so that usually helps to bring a lot of moisture in the region. And we still get a lot of shear at this time of year. Unlike Florida, they don't get a lot of fronts in summer, but we can still get fronts in summer. And so as a result, these frontal boundaries and a little bit of shear help to make thunderstorms a little bit stronger at any other point of year, just because we have better instability. I want to highlight again our graphical hazardous weather outlook. In the winter time, this flips over to like extreme cold and freezing precipitation and things like that. But in the summer season, it swaps over to each of the different severe thunderstorm hazards. These are pulled directly from the Storm Prediction Center and mapped to our forecast area. So even in cases where a marginal risk is just clipping our area, these maps will highlight those type of things if it's barely clipping into our region. And of course, it also has potential hazards for lightning or excessive rain marked in there as well. It's been an experimental purgatory for quite some time, but it's still a very handy resource, I think, in helping you understand different storm threats. As a reminder, as we look at these different storm threats, that the Storm Prediction Center, the experts at forecasting severe weather, use this 6-tiered scale for measuring thunderstorms. Of course, the general thunderstorm is just labeled 0, indicating generally no severe weather is anticipated. And then you have the marginal to high risk category system that highlights both the duration and also the extent that you might expect severe weather, and then finally the intensity. So it kind of looks at those 3 different things of timing, how widespread, and how intense. And so generally the higher you go, the more dangerous of a situation it's likely to be. And of course, they map all these features. So you can figure out where statistically or probabilistically rather, the chances for severe weather is highest. And they break those down into specific percentages. Over time, this has become more and more driven by ensemble forecast systems. And even machine learning is able to provide statistical outlooks based off of certain variables. So more and more, these type of probabilities are literally becoming the percentage probabilities of receiving these type of hazards. So overall, like even since 2020, when these first began like this, where it was ranked out even on day 2, it's become more robust over the years, and what we're able to forecast in terms of probabilities. So just a quick reminder on tornado watches versus severe thunderstorm watches. Tornado watches indicate that there is at least a moderate potential. As long as there is a moderate potential for tornadoes, it will always be a tornado watch that is issued. However, if the tornado threat is low and other threats are much higher, then you'll have the opening for a severe thunderstorm watch. But as long as it's moderate, always tornado watch. Whenever the watch is about to be issued, the Storm Prediction Center will outline their thoughts on the need for convective watches. And sometimes they'll provide helpful notations, radar imagery, and things like that to indicate what forecasters are observing before an event is happening. And so on the leftmost image, I have their mesoscale discussion that was before a severe weather outbreak on May 4th of 2018, where they mentioned the severe potential and the likelihood of issuing a tornado watch at 80%, kind of giving a view of how much they think they need the tornado watch within that bubbled area. And then as a watch is ongoing, they'll sometimes provide updates on how everything is looking. And so this is for that same day on May 4th of 2018. And so their kind of remarks are how there's still a damaging wind threat along this little bubbled area as things are evolving. If you've ever wondered, the Weather Prediction Center, or WPC, they have this for heavy rain and snow too. I mean, I will say a word of warning, there's a lot of meteorological jargon that is often in these. I wouldn't expect everyone to understand what's happening in all of this. But sometimes it's a fun read in terms of just getting a sense of what forecasters are thinking and feeling, where there might be areas of uncertainty in the messaging. So sometimes it just gives you a little bit of insight into like where the forecaster is leaning onto the primary threat and where how they think models might be handling things and features like that. But those are the mesoscale discussions. Once we get to the severe warning, just a reminder on our criteria. Severe thunderstorm warnings are for thunderstorm wind gusts to 58 miles per hour, or if there's significant wind damage that might be expected, say for like trees and power lines. Hail greater than 1 inch in diameter. When it comes to tornado warnings, we're looking for Doppler radar indicated rotation, confirmed reports of tornadoes from, say, spotters or the media. And then for flash flooding, we're looking for at least 6 or more inches of flowing water on roadways or rapid rises in waters that'd be a threat to life and property. As we get to each of these different tiers and categories that we have, just as a reminder, the base severe tags actually do not trigger the wireless emergency alert system. And even the considerable tags on severe do not as well. However, I will say that the flash flood products, if we do hit this, it will trigger the wireless emergency alert system whenever it hits the considerable tag. So for instance, this last Wednesday, for those considerable flash flood tags, your wireless emergency alert systems should have gone off in theory if you have that turned off, or if you have that turned on your smartphone, then you should have gotten it. If not, double check that your smartphone does not have those turned off if you want to receive those type of alerts. I understand sometimes they can be a lot, but on severe weather days, I'd highly recommend having your wireless emergency alert system on. So those tags are really important for us in forecasting severe weather. Usually we're gonna 9 times out of 10 be running with just the baseline tags. It's maybe 1 in every 10 or so that we will be applying things like a considerable tag. And those destructive or high tier systems, those will be coming out usually once in a blue moon. Like those are, the destructive ones are especially known for being deadly. We try and save the destructive for something that is eminently life-threatening in such a way that is beyond what a base or considerable might offer. So we've kind of reviewed here the different severe weather operations, like the progression from outlook to the actual event. We've reviewed the climatology. Let's now quickly review here the environment and how it helps to shape the storms and their sizes. Typically, when we're dealing with a single cell thunderstorm like this little guy here, you're typically in a low shear environment. You may have plenty of instability, but there may be some mid-level dry air too. So all of that heating is enough to help a thunderstorm billow up during the afternoon. But as soon as the daytime heating is gone or the thunderstorm has rained itself out, then it simply dissipates. Now, sometimes you have sufficient shear and dry air in place, but you have plenty of instability. Sometimes it just takes one thunderstorm in those environments to be able to develop some level of rotation. Some single cell storms in the right environment can still result in these situations where you can have a single cell supercell. Oftentimes, discrete convection like this, where it's kind of separate from any features like a line, is actually a little bit more conducive to rotation, once you build these longer, broader lines like the squall line down here, it's sometimes a little bit harder to develop that inflow on the right-hand side of these kind of squall lines to help propagate or help these different tornadic supercells to grow. However, of course, you can't always get embedded supercells into linear features as well. If your environment is very moist, where you have plenty of moisture around, but you may not have a lot of shear, then you may end up with situations like this, where you're having a lot of multi-cells. Oh, that's the wrong color to pick. I was trying to pick a better color maybe to highlight that. Let's go pink. So with that, you may get large clusters of cells in these environments. They'll often drop outflow boundaries where you can get new convection to develop right along that outflow boundary, as long as there's a little bit of warm, weak inflow in them. Usually with these, we're talking about flash flooding, looking for any, it's hard. You're playing whack-a-mole often with these, where you're trying to find the one cell in there that's the strongest and most likely to produce severe weather. And then of course the squall line is a type of multi-cell storm. But usually there's a little more shear, and so it results in this more organized linear feature. And then on the highest range of the multi-cell type thunderstorms are your bow echoes, your large mesoscale convective vortices, like the 1995 Adirondack derecho, where you have a lot of shear in the environment and usually a lot of instability. And so as a result, you get these lines, and then from the shear, you usually wind up getting a little bit of this vortice here at the top of those lines. If you don't have too much directional shear, it may just end up being a nice straight line, as opposed to this that you can easily see a little comma, like right at the top of those lines. All right. And so, of course, storm structure is going to change over time. This will be based off of your shear. Do you have unidirectional shear, or do you have directional shear? Those type of features will play a large part into the evolution of your line, as well as how much dry air and how much instability you have in your atmosphere. And so generally the smallest scale is going to be that single cell, where the downdraft eventually overtakes the convective updraft, and just usually only results in minimal damage. We've kind of reviewed already the multi-cell and where flooding is usually the big issue. Sometimes tornadoes can be an issue if sometimes the outflows interact in such a way, but usually multi-cells, just looking for heavy rain and potential flooding. The squall line, of course, the jargony term, the QLCS, quasi-linear convective system, has its own threats. Usually the intense winds of these, just based off of their motion, where they're usually moving quickly off to the east, usually means you might get very fast winds for 30 to 60 minutes and then you're done. Usually they're not producing tornadoes, but they can. Usually if we're seeing these little embedded notches or kinks in the forward, or sometimes even back behind, that can be indicative of spin-ups that may quickly take place within these systems, but usually they're not known for producing too many tornadoes on most occasions. Again, as we go back into this analysis of more radar stuff, I always want to remind about shelf and roll clouds. I still sometimes see a few of our spotters on social media who will say they're seeing wall clouds, but they are just seeing a shelf cloud. Want to highlight again the difference between the two. And so a shelf cloud is not a wall cloud. It's going to stretch over a large part of the horizon, where a wall cloud is usually going to be a very small area of a thunderstorm. So this only highlights a shelf cloud, and they are formed as strong downdraft winds or say rear inflow jets are moving in. As they interact with warm inflow, they just create these little turbulent rolls that move across. And as there's a lot of shear on the axis of it, it spreads the canopy of clouds out in this kind of nice, very photogenic manner, that is indicative of the strong winds that are about to impact the region. And when you get to supercells, they're mainly known for their strong mid-level rotation. We apply that name when we note that. And so usually with supercells, you're gonna see a lot of striation within them. You may even see a little bit of rotation as shear is helping to help the parcel kind of rotate as it moves up into the thunderstorm. And where the wall cloud is going to be anywhere where the updraft is in coordination with the downdraft. This isn't the best view of a wall cloud. There's no real wall cloud to be seen here. I don't spot one within this particular case. But in this instance, if there was one, it'd probably be off camera here. As you can see precipitation falling just by the reduced visibility here. Other things you might note, just a reminder, if you see any different colors, like you can see some of the light blue shading here. In this case, this is probably where you have some hailstones within the thunderstorm. So again, if you see any different colors within your thunderstorm, you may be looking at hail within there. As a reminder, supercells last a little bit longer. The directional shear helps to separate the updraft and downdraft. And so as a result, that longer life cycle also means larger hail. Usually supercells can produce hail in the 2 to 4 inch range and will last a little bit longer. But only about 1 in every 5 will produce a tornado, usually only about a 20% chance that any might statistically result in a tornado developing. They're very well known for their structure. As we kind of go into the radar side of things, just kind of a reminder that they consist of a hail core where strong inflow on the right side of your hook echo is then being expanded outward. So this is high up in the sky. I'll kind of note that with the dashed line here. So this is moving up higher into the sky. And so as these winds are fanning out, you'll see this. You've got the V notch, and that helps. That shows up on radar due to that diffluent wind signature, where the winds are fanning out in the supercell. And so as a result, you have very good ventilation in the storm to create very heavy rain and hail. And so you have these downdraft winds. And so as you get to the downdraft side of the thunderstorm, as they rotate into the up and reach that interface of the updraft, usually somewhere between the hail core and where you start seeing that hook is going to be where your tornado is going to develop. The debris ball appears to be rotation, but it's actually not the debris ball appears to be precipitation, but it's actually lofted debris, which is very reflective to the radar. And we'll go over a little bit more about the signals on what all of that means. As mentioned, the wall cloud is going to be a very small part of the thunderstorm. Even this schematic, you can see the difference between the shelf cloud and the wall cloud in terms of its distance. It's going to make up a very small piece of the thunderstorm. If it's a very strong rotating storm, you'll be able to see the clouds turning within, like this one. This one has very clear rotation within this one. And so you have the precipitation falling. And then you can even almost see where some of the downdraft is occurring on the backside of this storm. You can see this area of lower visibility. This is probably dust being kicked up by the downdraft. And so probably coming out from here and into the page are these as this inflow into where this wall cloud is happening. So this one's a very good picture of what that looks like. The issue with our area, this is an example from the plains, but up here, I highly doubt anyone will ever see a true schematic like this of a supercell. Oftentimes we have variable terrain, there's a lot of forestation, and there's a greater likelihood up here that the wall cloud is going to be rain wrapped. And so as a result, it's going to be very hard to find picturesque supercells up here. So let's remind ourselves a little bit about radar basics. Radar is sending an electromagnetic pulse out, and the energy that's reflected back is the reflectivity that we see on radar. The more objects that are out there, the higher the reflectivity is going to be. So we use it to track the motion and movement of rain, snow, or hail, but it can also send back targets like birds, insects, and other debris. Radar is separated into the two different fields of reflectivity and then the velocity that it is moving at. Reflectivity's main function is to tell us the storm's intensity and its structure. When we're on the severe weather operations floor, we're looking for kind of two things. We're, of course, looking for a lot of these purple and pinks, which I guess I need to change the color of the pen now. We'll just go back to straight black here. A lot of purples and pinks are usually indicative of either melting hail or hail. Other things that we're looking for are these sharp gradients where colors are rapidly transitioning. So this is probably where you have a little bit of a downburst starting to take place in this thunderstorm. Other structural features we're looking at are things like bounded weak ecoregions. That is usually where an updraft is happening. So something is moving up into the atmosphere, whereas everything else around here is moving down. That's usually indicative of something a little bit more happening within the storm. Velocity helps us to learn about the wind speed and flow that's in a thunderstorm. So anything that's green or those blue cool colors are going to be objects that are moving towards the radar. Anything in red, any warm colors are going to be moving away from the radar. And so whenever we see features like this, where we're seeing rotation in a thunderstorm, if the reds and greens are right next to each other, that's what we call gate to gate. So in other words, any of these little kind of, you can see how all of these different objects are pointed towards the radar. That's just a fancy word, but this is just the next line, the next column over in these different radiuses from the radar. So you can kind of think of it like a little bit of a grid. And so you could call this like gate 1 or gate 2 or whatever you want to call it conceptually. And so if we see winds moving the opposite direction from each other off of these different gates, that tells us rotation is happening. Conversely, if we're dealing with a situation where it's in the same gate or same column, but it's moving in a exactly opposite direction, this pure divergent signature where winds are moving just purely away and towards the radar, that's indicative of the downburst wind event. So in velocity, we're looking for those two things. We're looking for where winds are coming together, where winds are moving apart, and where things are rotating. We're looking for those type of features within these storms. Usually the larger the area, the better it is. Like for instance, I'll just kind of take off of the edge of this image here. This is bad data here. And you can see how it's really gritty and has something is, there's some kind of artifact there that's causing the radar to think that there's this large wind moving toward the radar. That's not there. But in general, we're looking for like areas that have just much stronger like signals, like sure, like some of these pixels there are rotating, but really like this one is really, this is much larger, a significant signal. So oftentimes in this, we're looking for, are we looking at small dots or are we looking at very large concentrated areas? That usually is helpful as well in analyzing severe weather. One reflectivity note, we've already highlighted the bounded weak ecoregion. The bounded weak ecoregion is helpful in identifying supercells. You may see it on the lowest slices, you may not. It depends on what area you're looking at. So a slice of the radar, I should explain that term. A slice of the radar is simply a a different elevation. So one slice of the radar is the half-degree view, another slice might be the 1.3-degree view, another might be the 2.8 view, whatever. We call those individual things a slice. And so if you were to look at the 0.5, you might see the donut. But if you were to look all the way, say at 4 point whatever, you might only see just this area of red and pink associated with this. It's a bounded weak ecoregion when you see this over multiple scans where you have this area of low reflectivity within your thunderstorm, where then you have just right on top of it, you've got high reflectivity, and then you've got high reflectivity on either side. And so that's why it's called bounded, because it's kind of in isolation within the supercell. And so kind of imagine like this is the broad part of the plane, the outside this kind of view, you have stuff moving up and into this area, whereas down here you'll have rain driving a downburst here. Excuse me. And so this will be the area where we might look for things like tornadic development to take place. And so usually atop the bounded weak ecoregion where you have this strong area of ascent into a thunderstorm, usually this is also going to be about where you'll start finding your hail core. Things like this, like 55 to 60 dBz, this very high reflectivity is likely indicative of hail forming within this thunderstorm. And so the bounded weak ecoregion provides us with an idea of whether or not we're dealing with a supercell, and will usually be a sign that you're going to have large hail possible in the thunderstorm. Another important note about the radar velocity, sometimes you're going to have to do a little mental math. I've called them gates. Another name is the different azimuths of the radar. So each of the different pieces of the circle as the radar is spinning, each of the pockets between that are known as their azimuth. If an object is moving directly into that radar beam, it's going to be a lot more accurate at determining its speed. So if it's moving like this directly towards the radar, it's going to accurately determine the speed of the object moving towards the radar. However, if the radar is over here and the object is moving at a bit of an angle, it's going to underestimate the speed. So that's something that's really important for us as radar operators to remember, that say, hey, our radar is up here, our Colchester radar is scanning the environment, and we have a storm moving from west to east, say in Rutland County. What's that going to do for our wind speeds? It might say 30 knots on the radar, but because it's moving at an angle from the radar, usually we have to apply a factor this, so it's probably closer to 45 knot winds in those scenarios. So that's an important challenge in forecasting radar whenever we're seeing these lower wind signatures. So this might already be 45 knots, but it may not be at Rutland. So I know a lot of people probably are aware that it's just easier to forecast severe weather warnings here in the Champlain Valley near Burlington, because it's so close to the radar and because storms are typically moving directly towards it. It's a lot harder down in Rutland and Windsor County, just because stuff is usually moving at an angle from the radar. So there's a little bit of mental math that's involved. That's why sometimes you'll see meteorologists use storm relative motion as opposed to just the pure base velocity. And so that's going to be something that'll help you mitigate that factor. But it's also useful when you're trying to look for rotation storms that are moving very fast. So just kind of keep this in the back of your mind whenever you're looking at radar velocity and you're seeing storms move at an angle. Just know that the winds may be underestimated as they move at that angle to the radar beam. The velocities, there's more than just looking at the downburst. We've shown the divergence signature, but there's a couple of things that we can look at beforehand to measure whether or not a downburst is possible. It's important when looking at radar, not just to look at the lowest scans, but to also see what's happening up higher in the sky. Sometimes we call that looking upstairs. What's happening up at the higher levels of this thunderstorm. One of the features that we look for is what's called mid-altitude radial convergence, or MARC for short. Downbursts are possible whenever you're looking at these scans that are higher up, whereas a downburst signature has a opposing wind direction where they're moving opposite. In the case of MARC signatures, you'll see areas that are moving directly towards each other on the radar beam. And so usually when this happens, that wind is heading straight down to the ground and will usually produce downburst winds. This is probably the only way you can try and get a downburst wind event before it happens. And you're probably only going to get maybe 10 or 15 minutes of lead time on this. They're very finicky. It takes about a 25 knot difference to be able to create this. And so it's not a strong signal. It's not like these massive 100 knot things or whatever. They're usually subtle features that develop very quickly and then go away. And so these are hard to find. This is one of the more challenging pieces in radar operations to be able to find it. But as your storm is intensifying, you have this, so this is just a very micro scale view into the thunderstorm. It's got this small embedded circulation up and down into the thunderstorm. And so there's an overturning or this downdraft in the thunderstorm, and then you have the inflow into it. And so that's what creates this area in the mid area of the thunderstorm where you can see those subtle, these subtle velocities moving towards each other. The other piece of radar velocity that we can use at the operation level is looking for what's known as storm top divergence. And so what we do with this, so think of your thunderstorm, you're looking up at your cumulonimbus and it's high up in the sky. Your radar can do likewise, but at a certain point, the radar looks over the thunderstorm. And so we look for the point on the radar scan, the highest point we can possibly see in the thunderstorm. And then we switch over to the velocity view. And in especially strong thunderstorms, it will show a divergence signal where you have both wind moving toward the radar and wind moving away from the radar. And so whenever you see this, your storm is ventilating. This helps the updraft of the thunderstorm. Usually we're looking for, at this point, values greater than 80 knots. Whenever we see, say, winds moving, in this particular instance, I think this is about 90 knots moving away from, or moving towards the radar. I think this is about 30-ish knots, these colors here. And so you add these two numbers together, they're additive. So 90 and then 30 makes that about 120 to 125 knots. This is a very strong instance. I've only ever seen these numbers these high, a handful of situations up here. But this is one way we can estimate the potential for a strong downburst, or sometimes even hail. This is one of the ways that we can try and get out ahead of it, because what comes up is eventually going to have to come back down. So if we see a strong updraft like this storm top divergence signature, there's more likely to be overshooting tops that you can see off of satellite or from a spotter, and will usually result in a stronger downburst wind in these type of situations. So these are two important radar signatures that say any kind of Skywarn spotter can look for. The MARC is going to be harder to find. it's a much more subtle signature. Sometimes I'm just I look at actually other pieces of radar information to try and find a downburst, because the mark signature is usually too much. I have to spend too much time analyzing it when it comes to making rapid fire decisions. Trying to squint my eyes and find these is sometimes a little too much, and so it's a note, but it's not going to be something I'm going to look for on a daily basis. But if I see things like storm top divergence, I'll usually take an eye on that. Now, we've mentioned radar slices, and what you can do is you can make these into composite images, and so that's exactly what composite reflectivity is. It's taking all the different slices of radar, it's calculating the highest reflectivity values, and it's plotting that onto your weather maps. So composite scans may wash out features. Oftentimes a composite reflectivity image is going to remove the supercell, that hook echo, because it's going to be looking at multiple tilts. However, I think the composite reflectivity, one of its best strengths is that at a glance, you can tell which thunderstorms are probably producing hail very quickly in these. They're also useful for rainfall estimates because they provide a broad view of what's happening in the thunderstorm. They're also going to be helpful for radar rain estimates. Now, when it comes to looking at severe weather, looking for rotation, storm top divergence, looking for any of those mid-altitude signatures, the scanning strategy of the radar is very important. Each scanning strategy is going to be used for different things and to highlight different weather phenomena. And so we have some level of ability to choose what radar scan we want to stay in. Usually this is the what's called a volume coverage pattern, or VCP 35. This is our clear air or snow type view. So usually in the winter, there's not as much convection. And so usually it's beneficial to see mainly what's happening at the lowest levels, because higher up, there's nothing to look at anyway for the radar. And so mostly looks at the lower views. It's a slow radar scan too. We can run some extra supplemental views, but in general, this is kind of our no weather on the scope. Things are nice. It's a clear weather day. Usually we're on just the volume coverage pattern 35. When it comes to severe weather, we have a few choices. All of these different scans run through anywhere from the base level tilt all the way up to 19.5, depending on which one. If it's a rapidly evolving situation, then we'll pick the fastest one we can. We'll pick VCP 12. It moves very quick, and so as a result, it's very helpful in looking at, say, like a tornado on the ground. However, it decreases the clutter filtering, so you're going to get a lot of range folding where you can't really see your velocities. So in some cases, we actually don't like using VCP 12 because sometimes it makes the close to radar scans, it can make it hard to see. Most cases when we're running severe weather operations on our radar, we're going to be using VCP 212 because this is going to be helpful for the supercells and the squall lines and things like that, while having minimal impact on your ranges. There's going to be some decrease in the overall accuracy, but in terms of seeing how things are changing, it's pretty valuable. 112 is another option. It runs a little bit longer at 5.5 minutes, or just 5.5 minutes. It has less range folding issues, so the quality of your data is going to be a lot better as a result. So usually like large scale systems that have like a larger velocity signal are going to be a lot better on this. But for most of our severe weather events, they're going to usually be smaller features, so 212 is usually the scanning strategy that we'll be using here at the National Weather Service in Burlington. Now you see you've got all these different options. You've got sales or what's often called MERL. This is just, I should have written down the acronym. I didn't write down the acronym. It's like something about supplemental, azimuthal, and then I forget the rest of it. And this is the mid-radial something or another. Sales, basically, however many, didn't mean to cut over that hard into it. The half-degree tilt on sales is run multiple times, say up to 1 time, 2 times, or 3 times, just this lowest elevation scan. The MRLE or MERL, what this does is it does a rerun of the lowest 1, 2, or 3 tilts. So it just runs an extra 0.5, an extra 0.9, and an extra 1.3. Because we have a lot of terrain and because a lot of our areas are very distant from the radar, oftentimes using MERL is more advantageous than a sales. However, I'll note that 1 MERL is the same exact thing as 1 sales. They're the same thing. If we're going to put anything into the MERL configuration, we'll either pick 2 or 3 based on whatever is the most important feature. So the scanning strategy that we choose is an important part of analyzing severe weather. Another important feature is dual pole. So what we're going to do here now in the next 15 to 30 minutes is explain what exactly dual pole is. So this is something that's really neat. When we installed radars with the National Weather Service modernization, these were actually all installed in the when we began placing them in the late 1980s and early 1990s. But a lot of the applications of dual pole wasn't really understood until the 2000s even. So some of this is still actually relatively new meteorology that's still being researched to this day. But radar is actually an acronym. If you weren't aware, radar is an acronym for radio detection and ranging. And so the pulse that it's sending out is a radio wave. And so with that, there are different polarizations with each of the different beams that are sent out. And before we got to the Doppler radar that we all know and love, it only scanned the horizontal pulses, where it was just transmitting a horizontal pulse and coming back with a horizontal pulse. However, meteorologists quickly realized that it was beneficial to send a vertical pulse as well as a horizontal pulse. And so the radar is, with these dual pole configurations, is sending these different waves, one wave in the horizontal and another in the vertical. And that has a ton of useful applications. It helps us to easily find snow and rain versus hail. It helps us to delineate different targets in the radar just for precipitation. It opened up a whole new world of possibility, from correlation coefficients, which is essential to hail and tornado measurements, the spectrum widths, the hydrometeorological classifications, the specific phase difference. We'll go more into that here, and other kinds of features that help us more accurately estimate rainfall within thunderstorms. Dual pole is definitely one of the most important features to our modern weather radar. And so we've now mentioned correlation coefficient and the differential reflectivity, or ZDR. And so one of the things that we can see thanks to dual pole, I mean, hail is already quite reflective on the radar, but we can look for artifacts like these low correlation coefficients, the 3-body scatter spike, but we can also see the lower correlation coefficients in the hail core. And so we have those different features to be able to measure the hail's severity better than we could just with the legacy products. What exactly is correlation coefficient? So it looks at your horizontal beam versus your vertical beam and determines how much is it the same. It looks at uniformity. And so it answers whether or not your targets are different shapes and sizes. And so it'll help you pick out non-meteorological targets like birds and insects and buildings and other things and debris are going to be non-homogeneous. They'll be very different. So usually things that aren't weather targets are going to be very low correlation coefficient. Now, non-uniform meteorological things like melting hail or melting snow are going to be in this 0.8 to 0.975 range. So they're similar, but there's some different pieces in there. And then things that are all the same, like just pure rain, pure snow, those will typically have very high values. In other words, high correlation coefficient means your radar seeing the same thing across the board. Spectrum width can be used in conjunction with correlation coefficient. The spectrum width measures how variable wind speeds are, and so it shows turbulence and shear between each of your different scans. So sometimes spectrum width is used to show the quality of the data, but it also shows mixing of winds. And so when used with correlation coefficients, you can locate tornadoes on radar with a close eye. You have to squint a little bit, especially, and you can also see this feature at the leading edge of gust fronts because you're starting to kick up a lot of dust and debris, and so usually your correlation coefficient drops, and then you have the overturning winds ahead of your gust front that'll be picked up. And so this is the Middlebury tornado in March of 2021. You had an area of high spectrum width, followed by a debris ball that appeared soon after the debris signature there, soon after you had this area of increasing spectrum width. So the two go pair in pair. You can use them for a number of purposes, like getting confidence that there's a tornado on the ground. This is one of the really important ones. I mentioned how I don't always use things like the mid-altitude radial convergence signature or MARC. Instead, I prefer this measure, which is thanks to the capabilities of dual pole, the specific differential phase, or what we simply call KDP. This function is all about finding heavy rain. So high KDP means big drops. Low KDP means small drops, like really concentrated stuff. So you can detect wet microbursts by finding high areas of KDP that then slowly descend to the ground. And so this particular instance happened in July of 2019, where you had a thunderstorm develop. So you can see it come up, but then you have this area of KDP here that slowly makes its way down to the ground. And oftentimes you get new ones that develop downwind, especially when some thunderstorms are pulsing. So just kind of see how it moves down to the ground. That's an evidence for a downburst wind event happening. And so then you can also see the development of new thunderstorms by these values and looking for those as well. And so then you get a second collapse a little bit later in this type of event. So KDP, helpful for finding your wet microbursts. We saw plenty of these just a few days ago. Now, ZDR, this is one of the more complex pieces of what we can use with dual pole. This depicts the shape of the target. So a positive value indicates something is wider than it is tall. A near zero value indicates the target is roughly equal in terms of length and width. And negative values indicate your object is taller than it is wide. So hypothetically, if I were to ask, what is the ZDR of this cow? Excuse me. The value of this cow would be positive. So this cow is wider than it is tall. And then conversely, if I were to ask you the ZDR of this corn cob, you would say it's negative because it is taller than it is wide. And if I were to ask you the shape of the basketball, it would be roughly equal because it is about the same width and height all around. Now, thinking back to the shape of our raindrops, remember that rain, a lot of times rain is we like to view rain as, the classic teardrop shape. But realistically, thanks to gravity and thanks to the way it's falling, rain usually falls actually more in the shape of a hamburger. So usually high ZDR means you're looking at rain. ZDR of near zero usually means you're looking at hail, because hail is usually going to be roughly the same width and the same in the vertical. And when you're looking at these low ZDRs that are more like these corn cobs, you're likely looking at non-meteorological targets when you're seeing values that low. And so this has a lot of different functions. There's so much that you can do with ZDR. It's a little overwhelming sometimes because, as you can see on the right-hand part of the screen, it's really pixelated. There's a lot going on here. So sometimes it's a little hard to use, but you can see clearly the very heavy rainfall. You have high ZDRs here in this area. So you've got precipitation here. You've got values near zero here. So here's your hail core and things like that. And then downwind of that, you've got a little more rain. Unfortunately, ZDR is also affected by hail. So you can see like you've got the hail contaminating the images here. But this is one of the ways we look for bounded weak ecoregions. We look for that. We look for hail on this. You can find at the larger range of hail, like the giant stuff or gargantuan hail, you're going to be moving into the negatives on these. But for the most part, here in the North Country, we're going to be dealing with wet hail. So usually we're going to be looking at KDP values near zero, maybe up to 1 or 2. And if it's just pure rain, it's just going to be these high values that are going to be generally higher than 2. Like if we're dealing with snow though, we can detect dry snow versus wet snow. So wet snow that's melting will have higher ZDRs, whereas drier snow that is not melting will typically be a little bit drier on the whole in these situations. So very, very unique piece of information, a little noisy, a little hard to read sometimes, but a lot of functionality in being able to determine things like where your bounded weak ecoregions are and other characteristics of your thunderstorms. Now, I've mentioned that dual pole is really useful for precipitation accumulation and rainfall rates. The added depth of having 2 different wave orientations helps a little bit, and especially forecasting rates. It's not bias corrected at all. We tend to have a high bias in estimating the rain in our region, and it's prone to hail contamination. So it thinks hail is rain, and so as a result, it'll show really high values where hail is. But it's another tool in the tool belt. We're not going to usually make decisions off of it, but it's really helpful to pinpoint heavy rain. It helps us to detect meteorological targets versus non-meteorological targets. It's handy for beginners, but over time, it's hard to rely on this. And then the other neat thing that we've kind of mentioned how our radars kind of have 2 different pulses. We can benefit from stitching the information from multiple radars into one. And so that's called multi-radar, multi-sensor. And so you can refine these elements even further by applying these different radar applications to your storms. You get the composite reflectivity, just like the standard radar,
but it overcomes the cone of silence by using multiple radars, and gives you just a better definition overall across the region. You can get the estimated stream flow based off of different hydrologic models and the rainfall rates that MRMS is putting out. You can do this with one radar too, but it's so much better with multiple radars. Same thing with the maximum estimated hail size. You can do this with one radar, but when you start adding multiple radars into the equation, you can do even better and get more accurate. So with that, we have the mesh multi-estimated hail size and vertically integrated ice, which basically looks at all the different scans off of other radars and basically says how much rain is in an area. And then the maximum azimuthal shear, this helps us find rotation in supercells and gust fronts. You have more precipitation estimates based off of your radar, and even algorithms to estimate severe thunderstorm potential. So this has a lot of neat functions. We can look at specific levels. Say we're most interested in finding the height of the 50 dBz or 60 dBz from multiple radars. And we can use this to get a jump start on lightning. I usually look for certain reflectivity values at certain levels to find the development of lightning. It's not airtight. There's going to be some misfires or some that will produce lightning before anything ever gets to the layers that I expect. But you can look at layers like the -20 Celsius level where the temperature is that cold. If you start seeing high reflectivities in that area, you might be able to forecast hail potential in a thunderstorm with greater accuracy. Stream flows, like I've mentioned, you can look for where water is going to most likely respond. It uses the MRMS rainfall estimates and basin geography in a model to forecast basically how much excessive water you're dealing with. So this is useful for flash flood detection especially. There are 3 different types of models. The CREST model is kind of your standard weather situation. You're not really prone to flash flooding, kind of your normal day. The SAXMA, which is based from like a Sacramento, California model. This is to deal with complex basins and very rugged terrain. We actually don't have quite rugged enough terrain to make the SAXMA the most useful in our region. And then there's the hydrophobic for dealing with bird scars or saturated soils. So now after having dealt with so much rain this last Wednesday, I'm pretty much going to be using hydrophobic models in terms of finding where the most flash flood potential is likely to be at. So you have these 3 different ways that you can use with MRMS rainfall to forecast flash flooding. The mesh or maximum estimated hail size and vertically integrated ice helps you find your largest hail sizes. It tends to overestimate just a little bit. We usually knock off a 1/4 inch off of the estimated values off of these hail algorithms. It also will struggle on days where we have graupel or tiny hail in early spring, like mesh is not going to detect it. And so usually we kind of steer away from mesh when dealing with those April showers that have pea-sized hail in them. Mesh isn't going to be very useful for those days. So these values here that I have marked would be around pea to dime-sized hail. As you start getting into your reds and purples, you start getting into severe hail, usually on color tables related to your hail size. Now, this would be something a little more high-end. This is not mesh, sorry. This is vertically integrated ice now. Oftentimes we use this to detect downbursts. It usually helps you find where you have the most concentrated water and ice in a thunderstorm. And so usually some of this hail here will melt, and that process of melting will draw heat out of the environment and cool it, and that downdraft is strengthened by that cooling that's happening aloft as a result of melting hail. So sometimes we'll use this to help us find downbursts. The azimuthal shear tool, this one is more well known, I think, out in the even non-meteorological world, where you're looking at rotation. And so it's looking at each of the different azimuths for multiple radars, and it's really helpful to find your strongest supercells. Let's say you have 5 or 10 supercells that you're having to keep an eye on. And if you're starting to see the azimuthal shear value light up for one in particular, you're like, okay, that's the one I have to look at first. So it's a really good thing when you're screening and trying to find which supercell is the strongest at the fastest rate. So you can quickly locate those storms with the greatest spin. And if we aren't getting a whole lot of reports, like say we get like a report here, like a report down here, and like a report here, that may be hard to get a path out of, we can use the azimuthal shear tool to kind of say like, hey, that could be the potential track if we're hunting down whether tornado damage occurred. Now I've remarked here, it can also happen in squall lines. Often you'll just kind of see just high values that kind of propagate outward with the squall line, just as there's a little bit of shear that runs along the line. All right. The next thing, this is a relatively new thing. This is on its 3rd version. This is something that's called Prob Severe. I think this got started sometime in the 2010s. It sucks in various MRMS parameters to forecast the probability that a storm is producing severe winds, severe hail, or a tornado. This is most helpful again in ranking storms. It has its biases. Like we tend to find that it's a little aggressive when forecasting tornadoes and winds when there's nothing else that would help it. So it's not really good with shallow thunderstorms. It's not perfect. It has some problems, but you can see it has like flash rates, the shear values that are between each of the different gates. It's got how much environmental CAPE. It's drawing in pieces like that from mesoanalysis. It's looking at global lightning mapper even and finding the flash rate and if there's any changes in the density of it. It's looking at the hail algorithm, the liquid within the storm, and all of those maths are going into the probabilities of dealing with severe weather. And so then it highlights the areas that are of greatest concern for forecasters to take a deeper look at when forecasting these thunderstorms. And so really to boil this all down of between radar velocities, storm top divergence, the mid-altitude radial convergence, like all these different signatures that we see on dual pole from correlation coefficients to spectrum widths, it's all about really looking at all these different scans, watching the trends, how they change over time, and getting a sense for the environment and how the storms should behave in that from the soundings that we have, as well as the mesoanalysis that helps us to find boundaries. Models, radar, all of these things are never perfect, but they give us ideas on how they evolve. And so we look for things like directional shear and their evolution as we watch on radar. We're looking for turning winds, which are ideal for supercells or bowing segments. These are supportive also of extreme derechos and strong instability. The unidirectional or speed shear that creates these high speed rolls. And so as a result, you get these overturning of winds that create the beautiful shelf clouds, but also produce the very dangerous strong winds behind them and produce squall lines. And we kind of hunt for these features on a mesoscale. We're looking for these RAP mesoanalysis tools are one of the handy features that we use. If you've ever looked at a storm write-up, you're almost always going to find a mesoanalysis map from the RAP, which is just a rapid refresh forecast system. And so it does its own analytics as well. And so we'll look at values like how much CAPE and SIN the model's analyzing, and how much 0 to 6 kilometer shear it's analyzing. So say here you can see that the winds are mostly out of the south, and aloft, they're still just mostly out of the south or southwest in this kind of situation. The winds are turning a little bit more over Messina, so there's a little bit more shear here in the St. Lawrence Valley that's got a little bit more turning associated with it. However, sometimes if the frontal boundary is already crossed, your severe weather might be a little bit more limited, especially as you notice here, the values of instability are quickly decreasing behind this wind shift. So sometimes it's difficult to line up these features, but we'll look at these things to determine whether or not our shear is coming from the same direction or a different direction from what's happening at the ground. We're using things like these skew T's. It's called skew because we skew it based off of a logarithmic scale. And it's called a T because in the hydrology world, it's called a tephigram. And so we just kind of, we meteorologists have corrupted it to our own purposes because it's still a useful way to analyze the atmosphere. And we're looking for these specific soundings a lot of times in the evolution of storms and severe weather when looking at how radar might play out on any given day or what severe threat is most likely. The inverted V sounding is probably one of the more common ones that we'll see up here, where there's dry, low-level air, but there's plenty of mid-level moisture. And so anything that moved into this pocket, the evaporative cooling will enhance downdrafts. And so you're looking for, like you want to, if you see that blue line stand out, that wet bulb temperature, that indicates the potential cooling that your parcel can experience. And so the greater the gap between this blue line and the red line, you know how we talked about CAPE, where CAPE was the value of the parcel, which in this case is just like about right here. This is your CAPE value. In this case, this is what we refer to as decape, the difference between your red line and the wet bulb temperature within your sounding. That is what meteorologists call decape or downdraft cape. The loaded gun sounding is very rare here. This is characterized by a strong capping inversion, plenty of dry air, but then really good lapse rates, or in other words, this red line is moving to the left very quickly as opposed to very slowly. That is a good sign of the potential for strong downburst winds. What happens with these, it's called a loaded gun, kind of like you don't know when it'll fire is kind of the idea. So it's the atmosphere's version of Russian roulette, is can a parcel get over this stable layer? And usually what happens is with a little bit of daytime heating, your atmosphere might go more to something like this. If there's any showers or something in the morning, that can help cool this as well. And so then all of a sudden you have something that looks like this, where you have a very high amount of instability, where you're dealing with dry atmospheric conditions with high decape values. Usually there's a lot of shear involved too. These are usually involved with some of the most prolific events, and this event in particular here, this loaded gun sounding, is the sounding that happened before the destructive El Reno tornado in Norman, Oklahoma. And then finally is the wet microburst sounding. This will be the most common for us. On our recent day here on July 10th, just a few days ago, our soundings had these wet microburst appearances where usually your dew point is almost all going entirely to the left, where you have enough atmospheric instability. It doesn't have to be a lot in these situations, but there's enough of a gap that you're able to get some dry air to entrain into your thunderstorms and produce downburst winds. In particular, one of the more recent high impact wet microburst days happened in August of 2022, where a wet microburst occurred over Mariah and Westport in New York, or Willsboro, sorry, in New York, that produced near 80-mile-an-hour winds. So anytime where we're seeing the dew point, this green line, almost go just straight to the left without any deviation to the right. Is usually a good sign for a wet microburst. Satellites are also great tools for forecasting a thunderstorm's evolution. We've already talked about how the global lightning mapper uses a background brightness map and then looks at brightening caused by lightning to see lightning occurring from space. Any rapid increases in lightning density, as well as the number of flashes, usually indicates a strengthening storm, and you can get it before ground networks. You can also look at infrared imagery. And so usually infrared imagery, like the strongest storm here that was taking place in the middle of the, just on the northeast side of Kansas into Missouri, clearly stands out. And oftentimes you can even see things like the overshooting top here in this thunderstorm. You can see that it has very excellent divergence. You can see all these cloud tops from the anvil moving fast downstream. And you can even see some of the anvil cloud that is going against the strong southwest flow that you can see on the other end of satellite. And conversely, you can tell that these thunderstorms are a little weaker. They're still producing lightning, but are a little weaker. And then for other ones, you're looking for features like this, where initially it has fairly cool cloud tops, but over time it starts to wane, where those yellow colors go back to those blues. That helps you find where your thunderstorms are starting to die. So this helps us find the trends in how your thunderstorm is strengthening or weakening. Additionally, visible is the highest resolution data we can find. You can find boundaries. And so this one, you can see a gust front that is propagating downwind of these thunderstorms. And you see these others that are starting to fire off from the southwest. And as they meet it, they start to become particularly more intense where they meet with that boundary. So you can get minute by minute data on this. And what you can even do is at these lower levels, you can find the difference on each of these 1 minute scans. And you can estimate the velocity, say in like in miles per hour, knots, whatever. The speed at which those are moving, and sometimes you can find severe level winds that way. You can also see overshooting tops like this one right here as well. So this is also useful for analyzing that. Those type of features. You've got a boundary right here. You can find all kinds of things just off of visible satellite imagery. Really useful for watching thunderstorms develop and grow. Now, we meteorologists aren't perfect. We use cheat sheets all the time. We use these to find the typical parameters out of the atmosphere that is responsible for different weather conditions and wind threats like microbursts or these squall lines. Storm characteristics on radar, like what kind of correlation coefficients that we might observe from them. We'll go over features like that. We have cheat sheets for hail, of course. What levels of the atmosphere, what kind of ZDRs and CCs are correspondent with what kind of storm top divergence is located with it. And then of course, we have the cheat sheets for when we consider issuing tornado warnings and when we confirm a tornado is on the ground. We look for things like, of course, the classic hook echo. Does the hook echo correspond to the velocities? Are they gate to gate? Do you have a low correlation coefficient for your dealing with your debris? Do you have at least 30 dBz? Is it very reflective? And a ZDR near zero is helpful. Not necessary for confirming a tornado is on the ground, but it does build our confidence whenever we see those type of features on the ground. And you'll note that a TVS or a tornado vortex signature is typically going to fire when your rotational velocity is above 70. But typically, you can get tornado signature. I mean, you can get tornadoes out of storms with rotations as low as 30 knots in the lowest levels. You have to kind of base it a little bit. It usually only works for the lowest 10, but it's important to kind of know that you can get those lower values. And of course, we have our local studies. We have a few of our meteorologists, a few past and present, that kind of looked at the different ranges for reflectivity at different heights, and where hail and wind occurred. And so in general, whenever we see the 50 dBz starting to creep up above 22,000 feet, that's pretty much, that's a good sign for hail. Usually about 20,000 feet or so of 60 dBz, we'll be thinking hail in those situations. We've got at least a 50-50 shot when it's at least 20,400 feet. A little more variety in terms of wind. It's a little more driven by background flows and things like that. But in general, similar kind of setup. We're going to be looking for certain height in the thunderstorm to be able to determine whether or not an event is likely to be severe. All right, unfortunately, I think I haven't paced myself well enough, so we're gonna speed through these a little bit, but let's analyze a couple severe weather events in our area. First, we're gonna look at the May 4th severe weather event. This is the last moderate event to occur in our area and was the first to take place since 2012. So this event on May 4th of 2018 is one of the highest, probably one of the biggest severe weather outbreaks that's happened in our region in quite some time. And it's been about now 6 years since then. So on this particular day, the Storm Prediction Center had much of our area in an enhanced and moderate risk outlook, forecasting about a 10% chance of tornadoes across the region. None happened this day, but as you can see, the wind threat was forecast to be of greatest concern at a 30 to 45% chance. And then just due to the squall lines are usually not helpful for hail. Usually squall lines are mostly a wind threat as opposed to hail threat, but the potential was nevertheless there. On this particular day, there was widespread damage and some hail across the region. Most of the hail was on the north side, but there were some other reports, I think, that down in I can't remember exactly where, but generally an inch and a quarter near Potsdam, an inch and a quarter near Enosburg Falls, and another at an inch 3/4 even, and some smaller 1-inch hail in the Champlain Valley. But you can see the abundant wind damage that occurred as a result of thunderstorms that coalesced. They began to develop in the St. Lawrence Valley, and then over time began to coalesce. And so when they start developing in this line type feature, that's when you have your greatest chance for straight line winds. This was a very potent area of very potent upper level low. There was very high shear thanks to winds at 850 millibars. This is up just 5,000 feet off of the ground at 70 to 80 knots. So very high shear. And unlike most situations, we often deal with cloud contamination here. But you can see that on the south side of these overshooting tops, that you had clear skies for the most part. So very strong destabilization ahead of the frontal boundary with visible towers right along the gradient of thunderstorms and where you had that clearing. That is usually indicative of very favorable conditions for the straight line winds that took place on this day. Here's looking at these are different these are not slices, sorry, these different windows into these thunderstorms. These cross sections are 3-dimensional views of these thunderstorms. And so you can see that we've analyzed here the tilt of the thunderstorm. You can see how the high reflectivities are slanted along this cross section. And so that's showing you how strong the shear is. But here you've got relatively low reflectivities. So you had very strong inflow moving up into this thunderstorm. Even though it's being sheared, that strong inflow resulted in very high reflectivity. I mean, just look at the depth of this. Sorry, I guess nerding out a little bit. The depth of this being like near 10,000 feet on this. Just very strong wind signature there. Usually, of course, you want your hail signature. This at at 21,000 feet is sufficient for hail. Usually you want it a little bit higher up just to play safe. You might get it 50% of the time, 50%, it's like a coin flip. But just with how deep this is just showing that you have the very strong potential for wind. We've already shown this mini supercell before in showing the bounded weak ecoregion. Of course, you also, this was not as tall of a storm. It had only 60 dBz up to 22,000 feet. Even then it was maybe even closer to 55. Like this core was a lot smaller in terms of the purple bad kind of thing. But generally though, the supercells are going to perform a little better in the hail making department, just with the fact that you have the updraft continuing to support your hail core in this thunderstorm. And so this is the radar view of that miniature supercell that was in Richford, Vermont. It had a clear hook. It's sometimes hard to find clear hooks here, but a very strong hook echo with 60 to, there's a small pocket of 70. Usually again, when forecasting, you want to see large areas. So just 1 or 2 pixels is not always a great signature, but this would have been the storm that produced the 1 3/4 inch hail as it was moving from Enosburg into Richford. And we mentioned the separation of updraft and downdraft. So the downdraft is occurring about right here in your updraft within this section. And so there's your hail core within this supercell. And so then you've got the V notch is a little bit harder to see, but about like right there. There's your V. And then of course, characteristic with the supercell is the mid-level turning associated with it. So this mid-level cyclone it never produced a tornado, but it did produce very hazardous weather, downed a lot of trees, and of course caused that 1 3/4 inch hail. It was particularly damaging. Now here's one in Shelburne that produced 2 separate downdrafts. You had 60 to 70 dBz in the lowest levels. And when this happens, that's usually showing that you have melting hail taking place. And so the environment's losing heat to that melting hail and strengthening the intensity of the downburst. Very strong downburst for our region. You had 55 to 65 knot winds at 400 feet. So that is this is really close to hurricane force wind gust. So this is very strong for our area. You have values, this would have been about, unfortunately this notation is blocking it, but this would probably be about 40 to 45. And then this divergent signature is probably about 35 to 40. So down here in Shelburne, you probably had a downburst near 80 knots or close to 90 miles an hour at the epicenter of where this would take place. And so in this one, some of it's going to get lost to friction when it hits the ground and lost to going through the trees. So that may not be the exact wind speed that it fell at, but this was the image of trees that we showed knocked down that had those downburst winds associated with it. And then that propagated north as it approached Shelburne proper and moved up into South Burlington. It was a classic signature that came just 20 minutes later. Shelburne got hit twice on this particular case. One of the other things we highlighted that's important in looking at radar is the difference between small distances here. So you're going from like these reds and greens to blues very fast. You've got the back edge here where you have this area of more yellows as opposed to the purples here. And so you can see you've got your bow. You can kind of imagine your bow and arrow of strong rear inflow into the storm. And it shows up in the velocity with 55 to 60 knots descending into this thunderstorm. And so this downed a lot of trees in the Stowe area as it shifted east. So almost anytime you see like this little bowing structure and you have strong winds moving in the back side of it, like so, any kidney bean shape with strong winds behind it, probably are dealing with strong winds on the backside of these thunderstorms. And then as it was moving east further into central Vermont, one of the things that caused us to sweat a little bit were as it was about to exit the state, you had the line feature, and of course you can see there just a few notches on the front side with corresponding pieces of rotation. And so none of these produced tornadoes in our area, fortunately, but it was enough to cause us to sweat a little bit as this line was making its way east and out of the region. Nevertheless, just remember the radar is somewhere up here, and this is moving east. So radar is underestimating the wind speeds. So these may appear to be values of 30 to 35, but they're probably closer to the realm of 50, just due to the radar underestimating the beam as it's moving away from the radar. And then the last piece of the storm that we'll look at are these little miniature bow echoes. So we've pointed out how things can be linear, but sometimes they look a little bit more like this, where there are a lot of waves in between. And in this case, you have a lot of different rear inflow jets moving into each of these different segments in a line as the line evolves. And so you can see each of these different pieces of rear inflow that's helping give this line this kind of these different little bows in between. The danger with these, there's none in this instance, but hypothetically speaking, it'll be on these areas when you get these winds that do like this in the bow, you naturally make it a small area of turning on the north side. I don't see any evidence here, but when we're dealing with these type of storms, we have to keep an eye that there's not suddenly something coming in towards the radar. There's a little bit of one right there. I'll kind of erase this to re-highlight that. There's one small area where there could be some rotation on one of the bookends, but overall, I'm not seeing any on this particular scenario. But strong winds, nevertheless, this down several more trees. The next event that I want to highlight here as we put into practice some of the radar things that we talked about is this July 13th event last year. One of the higher end severe weather outbreaks, and it kind of quietly took place in scope of just because everyone was still dealing with just so many flood impacts from last year's event that this one just kind of slid under the radar, so to say, just because of how much worse the flooding was last year compared to this even high and severe event that included a tornado. And so let's look at some of the radar signatures on this event last year. I've got this satellite picture. You know, we talked about satellite looking for trends. Before the event unfolded, even east of Lake Ontario, this would have been, this is taken at 10 a.m. in the morning. Strong area of low pressure. You can see the broad rotation there. You've already got at 10 a.m. You've got strong thunderstorms developing on the east side of Lake Ontario. And you can see Lake Champlain right there. So we've got clear skies and plenty of time for instability to develop. You've got a few boundaries marked. You can see a few areas of embedded areas of stronger cumulus clouds. Really, we were ripe for a severe weather day. We had a negative tilt trough, and those almost always cause some kind of trouble. It was coupled with a jet streak, and so when we see this, that helps thunderstorms ventilate. Usually helps thermal packing. It makes fronts stronger, makes it a little bit easier for storms to focus in on an area. And so you had one jet streak here and another up here, and so a lot of air just moving, evacuating from the area. Very favorable for thunderstorms. I'll let the evolution on radar play one more time here. So you've already got the strong thunderstorms on Ontario. We've got a few out ahead of it that began to develop, that produced I think this one's the tornado producer. And eventually it becomes this line. You even saw briefly there was a vortex before it got ripped apart. This was another high-end severe weather day for us. So the first thing we want to analyze, let's use one of our dual pole capabilities. So this was a storm near Potsdam, New York. This produced a funnel cloud at about 2 p.m. This is a radar rotational calculation based off of MRMS. So this is a radar rotation, and you can see that this thing off of dual pole, it saw broad rotation. However, like the edge of it was like about right here and right here. So there were several gates between them. The radar rotation was broad. So that's usually not favorable for producing a funnel. Honestly, I'm surprised that a funnel was able to be produced out of this because it's quite far away. It looks a little better on the velocities, but only 20 to 25 knots, and being at such a long distance away from the radar, you need to start getting more into like the 35 to 40 knot realm before you can start getting a greater chance for tornadoes in these situations. So, but this produced a funnel cloud, and so there's the signatures for that. The storm here next that we're going to I'll take a look at. This was near Scroon Lake. This was a particularly impressive storm. This was a supercell. So it was a long-lived storm. It produced damaging winds up to 85 miles an hour. We went and surveyed the damage on this and estimated about an 85 mile an hour wind occurred with this. And there were multiple reports of 1-inch hail. A very impressive storm. It had 60 dBz up to 28,000 feet. And if you remember our cheat sheet that we referenced for hail, 20,000 feet is usually the median bar where you're going to get it like by a coin flip. So very, very strong storm that produced hail near Scroon Lake and this wet microburst around 5 p.m. in the area. And so now here's a view from the dual pole side of things again from KDP. I've got the reflectivity on the left, and then the thunderstorm core dropping from KDP on the right. And so you can see these oranges and these green colors maximize and then reach the ground. You can also see how you have high reflectivities aloft, but you can look below and it's mostly greens and reds, but over time, those reds and purples move closer and closer to the ground. So you've got a very solid radar evidence of a downburst wind event that happened here in this case. And so here is one of the particularly impressive pieces of damage that this did was that this moved this boat off of its, it was tied down, and it moved the boat and down trees. Fortunately, the trees did not go down next to the boat. So maybe in this case, the boat was saved by the winds, but the winds were sufficient to pick up the boat and move it by several feet. And then the next thing we're going to analyze with this event, let's look at the tornado that tracked from Benson, Vermont to Hortonia, Vermont as it crossed the Warrior Lakes. Unfortunately, the tornado was not photographed, so we had to go out and survey to find evidence of this tornado. It was an EF0 that produced 85 mile an hour winds as it tracked across the region. This one was very tough. The tornado developed a bit to the south of the mesocyclone, and so that was part of the difficulty. And the rotation also developed very fast. I have the radar scans just 3 minutes apart, and you go from about 20 knots or so of disorganized rotation, like, yeah, you've got a little bit moving away from the radar, you've got some stuff moving towards the radar, nothing to write home about. And then the very next scan, you've got 30 knots away and 30 knots towards the radar. You've got 60 knots of gate-to-gate rotation just right then and there. Very rapid evolution of this that kind of forces forecasters to make quick assessments of what's going on. So how do we know when a tornado is on the ground? Again, we want lowering, we want low CCs, low correlation coefficients in the hook. So here's now our hook. We want to see high reflectivity, but we want to see that high reflectivity that corresponds with where the rotation is. And in this case, the rotation and where the reflectivity were, they didn't really line up. So we had the downdraft that was apparent, but it didn't really match with where the rotation was taking place. So the radar scan here is like, yeah, we see the rotation in the lowest level, and it's very strong, but do we have any debris, and does it really match and line up? And not really. So here's our tornado reports that we received, and what was frustrating is that the tornadoes reports, as you can see, there's the hook. The hook is like way off here, but the tornado reports were down here. So the reports that we received from this tornado, it kind of perplexed us for a little bit because we didn't have, it didn't line up with the reflectivity. Additionally, we're looking for low correlation coefficients, but I'll kind of let this loop here. So there's our tornado report. These values are high. These are close to 1 in these situations. Typically, we want to see lower values, like these blue colors or these green colors start to appear, and that wasn't present. So from a radar perspective, this would be very hard to confidently say that a tornado is on the ground. So I think the forecaster, they did put out a tornado warning. You can see the box, and that I think was the right call given the how strong the rotation is. But could we say that a radar has confirmed a tornado is on the ground? It'd be a shrug at that point. The radar velocity, the radar coalition coefficients, and the way that the velocities don't correspond with their reflectivity made that a relatively low confidence tornado warning. But one did occur, so that's why we do surveys. That's why we check things out when we're not sure. Now, eventually, a large bow did form into central Vermont. This was as the tornado, as the cell that the storm that produced the tornado. Eventually, it just became this area of broad rotation overall. So it just kind of grew bigger into this more broad vortex. And so you had it drive strong winds on the backside with trees down in Bethel and Randolph and Braintree as this vortex moved. Of course, remember the radar is somewhere here up off the screen. And you can see your winds are moving southwest to northeast, where radar, the best viewing is from southeast to northwest. So these are underestimated values. So seeing this, which it never quite goes into these more bold reds, but again, probably about 45 to 50 knots on some of these velocity signatures here as it's moving at an angle to the radar. So these two situations are mainly to highlight these key bullets. Severe weather in the North Country is rarely clear-cut. It's very rare to see the bright and bold signatures on radar that areas in the plains are going to see that almost can confirm severe weather like tornadoes is happening. We have to use every tool in our toolkit to find boundaries. We have to use our surface observation stations, our satellites and radar tools with our mesoanalysis and understanding of our climatology to see what patterns we're in for. Models help drive expectations. High resolution models can help us figure out how things evolve, but we really have to keep an eye on everything and watching and using our understanding of how storms are most likely to evolve to be able to forecast severe weather. Beam blockage poses serious challenges, especially outside the Champlain Valley. And so really we often do rely on reports from our Skywarn spotters. We've gone over some of the dual pole features, how it has helped in a lot of ways to be able to recognize severe weather. Probably the most useful ones being, of course, things like correlation coefficients and the differential reflectivities that help us spot tornadoes and hail. But the radar science is evolving and is going to continue to be supplemented by things by satellite. So when it comes to reports, just a reminder on how spotters help out with that. Spotters, it's good when you're calling us to let us know who you are, where you are, the weather that you're observing, and what time it took place and how long it took place. It's helpful to report tornadoes, funnels, and water spouts. If you see any wind damage near or like at the time of the storm or soon after, let us know. Hail, measuring tip to tip. If you've got very heavy rain or flooding or heavy snow amounts and freezing rain or sleet, lightning damage, we received actually a lot of lightning damage recently, or if there's any weather-related injuries, that's helpful information to us to know. As we continue to analyze severe weather events in the region, it goes a long way in helping to match radar signatures to your reports. So that goes into our cheat sheets to, if we see like, hey, we've had spotters report consistently for these parameters, and we can tie it back to an event that helps us during an event and as we go through. I was gonna quiz everyone, but we're down to about 5 minutes and I wanna leave some time for you to ask some questions. So overall, I'm just gonna give you some reminders here. When a storm is moving at an angle at the radar beam, the velocity is going to what? I guess I should say be underestimated. So whenever whenever a storm is moving tangential to the radar beam, it will underestimate the value. These are some of the signs for hail in a thunderstorm. It's going to be reflectivities above 60 dBz, especially above 20,000 feet. Correlation coefficient values below 0.9. ZDR values close to 0, because remember, hail is usually going to be relatively nice and equal in length and width. And this one was more of the tricky one. The storm top divergence above 100 knots usually shows that you have a strong updraft that helps produce hail. So A, B, D, and F. Which of these radar signatures indicate damaging winds? I was gonna trick y'all by messing with the name here. The actual case that would indicate damaging winds is a mark signature, mid-altitude radial convergence, but the others are rear inflow jets, and sometimes your bounded weak echo region can help. Mileage will vary, but that can be one of the signals as well. And then what type of shear is conducive toward tornadoes? It's not sheer willpower, but it's going to be directional shear. That helps the turning, rotating winds that you see within your thunderstorm. And then finally, the 3 radar signatures that confirm a tornado is on the ground is going to be strong rotational velocity in excess of 70 knots in the lowest scan. Correlation coefficients of 0.9 or less, and with reflectivity above dBz, that is your tornado. That's your tornado debris signature, your TDS. And then you also want to see ZDR values near 0 by the hook echo, because remember, rain is going to be like a hamburger, so it's generally going to be positive, greater than 0. But if you have more of these lofted debris, like in dust and things like that, it's going to edge a little bit closer to 0, may even go a little bit negative as a result of that. Also, it helps to see vertical continuity of correlation coefficient. It helps if you see the debris signatures like this happening over a number of scans. If your scans are lofting debris to 50,000 or 5,000 feet, probably a weak tornado. The higher you see lofted debris, the stronger your tornado is likely to be. And so those were the review questions that I had. Sorry I didn't have time to quite make it a review quiz, but at this time I'd like to open up the floor. If you have any questions, I've got, of course, the question box. And so at this point, I'm going to review some of the questions that we have in there. So let me know what your questions are, and I'll start answering here. All right, so first question I see here, with the change of environment to global heating, can we expect more severe weather events in the future? That one's actually tricky. It'll be both a yes and a no situation. So we talked about our sounding profiles. I'm gonna just escape the percent. Oop, I didn't mean to entirely escape like that. But we'll escape to this. Find the sounding profiles right here. So the sounding profiles that we have. So we remarked how we want a lot of surface heating to develop instability, but one of the potential impacts from climate change is that a lot of the heating actually gets realized, or well, I shouldn't say a lot, but some of the heating gets realized in the mid-levels here, like at 850 millibars. So the potential is that we may deal with instances where we have more capped environments. And so in that case, we may actually not have as much instability to generate thunderstorms because we have more stable layers just due to the stronger mid-level heating. However, in the case where the mid-level atmosphere is cool, or like suddenly say like something drives the temperature there cooler, then that may increase the conditional threat down the road. But it's one of those things that's a little hard to determine. It's a little bit of a yes and no. So how can we in the field assess these different scans? As far as what you can observe off of your radar, you've got all different kinds of apps. Unfortunately, I can't recommend a specific app. We can't show favoritism towards a specific business, but there are some services that offer different products that let you observe the different scans from radar. Our own radar page offers some pieces of information. So like you can look at some of the different scans based off of that, but some of the products are limited to certain views. Honestly, I don't dig too often into it. It looks like what we see on, like I'm looking at just on my phone here at the website. I only see reflectivity, base velocity, sorry, the hydrometeor, the class of that, and then the different rainfall rates. I'm not sure if it offers the ability to look at more than just, well, you can look at echo tops. I mean, that's not much, but you can figure out how tall your thunderstorm is from that and get a little bit of a picture from that as to whether or not you have stronger thunderstorms. But from an echo top perspective, usually our echo tops here only get to about maybe 30,000 or 40,000 feet. But if we start getting about 50,000 feet, then we start looking a little bit more closely, because usually to get that tall a storm in this area usually requires a little bit more oomph and then updraft. I think one of the other things I think I'll point out, just in kind of reference to spotters, is we kind of, for about 3 to 6 months, anyone here in this office spends an intensive amount of time studying radar, studying these signatures, doing simulations and training. And then even then, after doing all that, we kind of coach our newer forecasters with observing these on radar, and then just going through those different training sessions with supervisors and things like that, just to get a feel for it and just get confident with reading these. And I don't know, I've been at radar operations now for 5 years, and sometimes I'm still like, what do you think about this one? Like, I'm not so sure about this one. So a lot of times, even us here on the floor are sometimes looking for advice on the different signatures that we're seeing and what we're viewing. I don't expect our spotters to be experts at analyzing these and pointing these out to us on radar. This is more, and the purpose of this advanced Skywarn course is to just feed you with a little bit more knowledge of what kind of is happening behind the scenes and what things we're looking at as we go through severe weather operations. And since I'm now looking at the radar, I see we've got a few things on the scope right now. And one of my roles today will be running the radar operations. So I think I'm gonna cut it here as far as this presentation. We're running a little over time here now, but I've got my contact information there on the screen. You can reach me at robert.d.haynes@noaa.gov with additional questions and feedback, because this is the first time in several years that we've done an advanced Skywarn course. So let me know if there's anything more you'd like to know or learn about, and perhaps we can schedule another advanced course down the line. Send me your questions anytime. Of course, we work rotating shifts and sometimes we're busy, so I may not always get to answer in time, and sometimes emails get buried, but feel free to reach out anytime. So thanks everyone for attending. I hope this helped you learn a little bit about what happens behind the scenes as we're looking at radar, and perhaps helping you in your Skywarn spotting to kind of recognize some of the more the radar signatures that let you know you're in for a little bit more of a significant weather event. So thanks everyone, and we'll close it out here. Hope you have a good rest of your Saturday. Have a good weekend, everyone.